So we're at the third and hopefully final tutorial on this homework. Okay, so now we're going to start looking at graphs, hopefully a little less involved. So we'll take 10, 11, and then that's it. Oh, wow, nice. Okay, so what do we have in number 10? We have a rotational kinetic energy versus angular displacement. And ignore these dots here, okay? That's not helping at all. So we're going to look at some linear plot between rotational kinetic energy, KE, and angular displacement, and that's theta. And I'm asking you to find net torque and applied force. Other information is that we have a radius of 0.2 meters. So how are you supposed to get torque? Usually when you hear torque, you're thinking angular acceleration, and you're thinking tau equals I alpha. And while that's true, that doesn't really help us here because neither kinetic energy or theta are in there. When you hear kinetic energy and you associate with a torque, you got to think in terms of work. Okay, so it's very easy to forget that, but work from a rotational standpoint, if you recall, well, any work is a force times a distance, right? So from a rotational standpoint, that translates to a torque times a theta. Okay, there's a direct, I did that way back in previous notes. So if I want torque here, then I can see that torque is W over theta, and W goes towards the change in kinetic energy over theta. So that change part's important because that's an indication. It's not simply a ratio of choose one kinetic energy and the corresponding theta. No, we need the change, so that's the slope, long story short. So the slope of that graph is that, and that should give you the answer given. Now, once we have the torque, we can easily do applied force because torque, by definition, is a force times the lever arm. The lever arm is the radius of the turntable, so the force is essentially the slope, okay, divided by the radius. So here, you might not think of it in terms of slope divided by radius rather than what you got here, but if it was a test question, they could ask you how could you use this graph to find the applied force. You would want to basically say slope divided by the radius. All right, this looks like a similar graph. Well, you notice the dots mirror the ones I had above. That's not a coincidence, but I'm not going to explain how that happened. Anyway, we've got torque, tau, and we've got time. And we want to know how would we determine the change in angular velocity, omega, so delta omega, for a solid disk. Solid disk goes towards I, right? I'm just going to jump right now. You look that up. That is 1/2 mr squared. Okay. M and after 0.6 seconds of time. So in other words, right here. So we have a graph that basically is centered along the 5, and we want to know at that point, as the torque increases with time, what has happened to our change in angular velocity. So we want to use the graph. All right, so this is a multi-step problem. And I started in that, and I said, we want to start by understanding what the change in momentum, angular momentum is. And the change in angular momentum comes from an angular impulse. And an angular impulse is similar to a linear impulse. A linear impulse is, right, if we know that delta P is an Ft, then a delta L is going to be not an F, but a tau, and times the time. Okay, well, here's tau, and here's time. So for multiplying them, that's nothing more than the area under here. Okay, so delta L is equal to that, is equal to the area. Now that we know that, how do we get angular momentum, or change in angular velocity? Well, delta L would also be equal to I times delta omega. Okay, just like delta P is m delta V. So I is 1/2 mr squared, and delta omega is what we're looking for, and this is the area, which is just or delta L is the area, so we'd say the area is equal to that. So delta omega will be twice the area divided by the mass times the square of the radius. Okay, and that gives us all our relevant information. Okay, so if you have any questions, we'll hopefully talk about it on Schoology or through a Zoom session.